Loudness describes how humans perceive sound energy. The loudness levels depend on the distance from the source of the sound. For instance, if someone was just talking quietly beside me, I could hear them really, really well. If they moved, say, a kilometer away from me and shouted, I probably wouldn't hear them at all. Even though they're speaking louder, they're producing more sound energy or using more energy, I couldn't hear them just because they're further away. Sound intensity is the amount of sound energy being transferred per unit area. So what that means is when you produce a sound, it starts spreading out over a bigger and bigger area. It actually travels away from us in all directions. So the same amount of energy is being spread thinner and thinner and thinner. And that's why it seems like it's decreasing. It's actually not decreasing, it's just spreading out more. Sound intensity is equal to its power divided by area. And we know power is how much energy every second is being spread over a given area. So on page 395, there's this cool little table there. And it just gives you an idea, well, what numbers are we talking about? So we have the threshold of hearing, and they give us the number value in watts per meter squared and in decibels. So the threshold of hearing, that's like the quietest little sound our ears can pick up. That's 0 decibels, or it's 1 times 10 to the negative 12. These two numbers mean the exact same thing. They're just two different units. For instance, if you're measuring 1,000 meters and a kilometer, you are actually measuring the exact same thing. Normal breathing is 1 times 10 negative 11. In decibels, we consider that 10. Now, every step on this scale is a step 10. So when I go from 0 to 10, that's 10 times louder. However, when I go from 0 to 20, I've moved 1 step, 2 steps. That's 100 times louder. If I go to 30, so that's 1, 2, 3, that's 1,000 times louder. This is what we call a log scale. You've used this before or seen this before in grade 10 science. The pH scale is a step of 10. Every pH greater is actually 10 times stronger. The Richter scale is the same thing when you're dealing with earthquakes. So another one is sound. So every step is actually 10 times greater. I like this one. Tornado, 1 times 10 to the 12, which is 240 decibels. An atomic bomb is 1 times 10 to the 13, which is the same thing as saying 250 decibels. We're going to try some examples now. What is the difference in sound intensity of a sound that's 10 to the negative 12 watts per meter squared compared to 10 to the negative 8 watts per meter squared? So what we want to do is look at the exponents and see how many steps apart they are. The easiest way to do this is we'll start at the negative 12, write it down, and go until we get to negative 8. So negative 12, negative 11, negative 10, negative 9, negative 8. And then you simply count the number of steps. When I go from negative 12 to negative 11, that means it's 10 times louder. If I go 2 steps, it's 100 times louder. If I go 3 steps, that's actually 1,000 times louder. But in this case, I went 1, 2, 3, 4 steps to get to negative 8. That is 10,000 times louder. The other thing we need to learn how to do is to convert from one scale to the other scale. And there's a little pattern here. There's a trick here. So it says convert the following into watts per meter squared. We're starting with decibels. So what you do is you always just look at you ignore the 0. So let's ignore the 0 and we're just looking at the number. We have the number 2. And all you have to do is just go 2 minus 12. And it's always 12. We're always going to subtract 12. Gives me negative 10. So when we write this out, it's simply going to be 1 times 10, and that becomes our new exponent, negative 10. So 20 decibels is the same thing as saying 1 times 10 negative 10 watts per meter squared. Let's try that again. You ignore the last 0. So what does that leave us with? That leaves us with 10. So you're going to go 10, subtract 12, Again, we're always subtracting 12. It's always a difference of 12. That gives me -2. So this is our new exponent. We're going to write down 1 times 10. Our new exponent is -2 watts per meter squared. There's our answer. So to simply convert from decibels to watts per meter squared, all we have to do is subtract 12, and that gives us our new exponent. Let's try this one. We ignore the back 0. We have 14, so that's our number. We're going to go 14, subtract 12, gives me 2 this time, +2. So I simply write 1 times 10 to the +2 watts per meter squared. You've just learned how to convert decibels into watts per meter squared. So we're going to try it the other way around. We're going to convert the following, which already start in watts per meter squared, into decibels. So before, what we did was we subtracted 12. Now what we're going to do is add 12. So when we're going the other way, we have to add 12. So you take the exponent. In this case here, it's -3. So -3 plus 12 gives me 9. Now remember before we ignored the back 0, we need to add that back 0 back in. So 9 becomes 90 decibels. Let's try another example. This one is 10 to the -7. So you take that exponent, which is -7. We're going to add 12 to it. So plus 12. So 12 subtract 7 gives me 5. But we don't just leave it at 5 decibels. We make it 50 decibels. All you do is you add the 0 back in. So we have 50 decibels. The last example here. The exponent is +6. So we take 6 plus 12. Well, 6 plus 12 is 18. You need to add that 0 back in, so that becomes 180 decibels. So when we're trying to go from decibels to watts per meter squared, you're subtracting 12. When you go the other way, when we're going from watts per meter squared into decibels, you add 12. So the magic number is 12.